So in chapter 1, we're going to talk about sets. Now, a set for our purposes is going to be defined as an unordered collection of objects. You've probably encountered sets before. For instance, maybe in an algebra class, you would see the set of integers. If you took calculus or pre-calculus, you're probably familiar with the set of real numbers. So oftentimes we think of sets as being some collection of numbers, but really a set can be a collection of anything. It can be a collection of people or of some variables or even a collection of other sets. It's unordered, which just means we don't really care about the order that we list the elements in. Now, we're studying discrete math, which means we don't care so much about sets like, for example, the set of real numbers, which we would consider something sort of continuous, right? There's some continuity there between any two real numbers. If you're looking at an interval of real numbers, even though that's a set, there's some sort of continuity there. We're looking at discrete math, which means we're looking at discrete objects. And so for us, it's enough to sort of list a set as just some actual list of elements. And so we often use curly brackets to describe the elements of a set. So here's a few examples of a set. I just named this set capital A. Conventionally, we usually name sets with capital letters. So I'm saying A is the set that consists of the elements 2, 3, 5, 6, 8, and 11. So there's no real rhyme or reason to these. It's just sort of seems to be a random collection of natural numbers. And so it doesn't really even need to be that the elements of the set follow a particular pattern, at least not one that's necessarily going to be clear to you. But there's some sets that come up often enough that we want to give them a particular name. So whenever you see this symbol, it looks like an N with like an extra line here, capital N. This is going to be the set of natural numbers. So I'm just going to describe it in words first. But this is just going to be the positive integers. So we can describe this as the set 1, 2, 3, 4. Okay, well, I don't want to draw them all, so I'm just going to use ellipses or ... to say that we're going to continue in this way. And this is a set of all the natural numbers. Similarly, if you see this capital Z with an extra line, this is going to represent the set of integers. If you're not familiar with that word, integers just means all of the natural numbers along with all of the negatives of those along with 0, right? So maybe you could write this as 0, plus or minus 1, plus or minus 2, etc. Or if you prefer, you could write this as one long line as ... Let's say -2, -1, 0, 1, 2, ... So it's just all the positive and negative natural numbers along with 0. Now, we say that any number or item that's in that set is called an element of the set. And so if we look back at our set A, well, 2 is an element of A, 3 is an element of A, etc. And so notationally we use this symbol here that looks sort of like a E almost, but it means 3 is an element of A. Similarly, this E with the line through it, right, this little symbol here means that this element 7 is not an element of A. And we can go back and check and see, okay, 7's not in there. 7 is not an element of A. All right. Now remember, we had said that a set is an unordered collection of objects. And so what that means is it doesn't really matter how you write out the elements of the set as long as they're all there. Right, so if I wanted to look at the set containing the numbers 1, 2, and 3, this is going to be the same set as if I rearranged the orders, right? 2, 1, 3, or 3, 2, 1, or there's lots of different ways that I could arrange those three elements. But since the order doesn't matter, this is just all the same set. We consider this to be equal sets. Sometimes, as we saw up above with a set of natural numbers and a set of integers, we use ellipses, that's a ... to indicate that there's a pattern in a set. So for instance, if you have the set, I'm calling it E, which consists of 2, 4, 6, ... that suggests to us that we're probably going to be continuing to increase by 2. Right? I went up by 2, I went up by 2 again, so I can guess that this is probably going to keep going up by 2. And since it doesn't end anywhere, I'm going to assume that it's just going to keep going forever. So this is probably going to be the set of positive even integers, right? Or the set of positive, or the set of even natural numbers as well would be another way to describe this. We could also describe a set as something like this. So this is 51, 48, 45, ... all the way down to 21. I don't know that there's a great way to describe this particular set, but I'm going down by 3 each time, and I land at 21, which is also a multiple of 3. So maybe you could describe this as all the multiples of 3 between 21 and 51. Or you could even, if you wanted to, just list out all the members of this set. So this ... indicates we're going to keep going down by 3 until we hit 21, giving us the set 45, 42, 39, 36, 33, 30, 27, 24, 21. Okay. Right, we see why we use these ellipses, because it can be tedious to list out a very long list of numbers. Notice that some sets are infinite in the case of E, right? There's infinitely many values here. This set is going to keep going on forever. You can continue to add to, etc. And so this is an infinite set, while other sets are finite. This set here had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 members to it. We would call that a finite set. Right now, it can be useful to talk about the idea of how many elements a particular set has, and that's what we get at when we talk about the cardinality of a set. So we say that the cardinality of a set A is the number of elements in that set. And the notation we use is we put absolute value bars around the set A, right? So this means the cardinality of A. It means the number of elements in A. All right, so let's do a few examples here. So C is the set 1, 5, 7, and 8. Well, what's the cardinality of that set? Remember, this notation, you put absolute value bars around the set itself. The cardinality of the set is just the number of elements. There's 1, 2, 3, 4 elements here. So the cardinality of C would be 4. All right, what about the set D? We have 3, 6, 9, 12, all the way up to 60. Now, just like we did on the last page with that set that I had called B, one way to find the cardinality would be to actually list out all of the elements, but yikes, it's kind of annoying and I don't really want to do it. So sometimes you can use some clever counting tricks to try and figure out the cardinality without actually listing out all of the elements. So here's what I would do. We're trying to find the cardinality. We're trying to find the number of elements in here. I'm just going to put bars around there to make it clear that we're looking for the cardinality. Well, I can find the cardinality of another set a little bit easier if I just take every element of this set and divide it by 3. So why am I dividing it by 3? Well, every single one of these numbers is a multiple of 3, which means if I divide everything by 3, I'll get a new set, right? 3 divided by 3 is 1, 6 divided by 3 is 2, 9 divided by 3 is 3, etc. All the way up to the last element, 60 divided by 3, which is 20. These sets themselves are not the same sets, they have different elements, but they do have the same size. They have the same cardinality, the same number of elements. And it's really easy to find the cardinality of this set because it's all the natural numbers from 1 to 20. So the cardinality is just 20. Right, so this was sort of a little shortcut way of figuring out how many elements were in here. All right, now finally we want to find the cardinality of this set that I'm now calling E. All right, so E contains 2, -5, and, oh, it's got an element that itself is a set, right? So we want to be careful here. The cardinality of E is the number of elements in E. So how many elements are in E? Well, here's my first element, it's the number 2. Here's my second element, it's -5. And we want to be careful. Do we want to count 1 and 3 as 2 separate elements? Well, technically 1 is not an element of E, and 3 is not an element of E. The element itself is this entire set. So starting with this curly bracket until this curly bracket ends, that's going to be one single element of the set. And so the element which is a set containing 1 and 3 is the third element of E. So we have 1, 2, 3 elements of E, which means the cardinality of the set E is equal to 3. Right? Here's the first element, the second element, and the third. So we want to be really careful if you're finding the cardinality of a set, make sure you know what the actual elements of the set are, right? So just to be clear, we could say that 2 is an element of E. We can say that -5 is an element of E. And we can say that the set containing 1 and 3 is an element of E. But 1 itself is not an element of E, and 3 itself is not an element of E. Okay, so now what could the cardinality of a set be, right? Well, we've seen a cardinality set with cardinality 4, a set with cardinality 20, a set with cardinality 3, and you could imagine how you could have a set whose cardinality is any natural number, right? Just count all the natural numbers up to that point, and you've got yourself a set with that cardinality. But you could also have a cardinality 0 for a set. And in fact, there's only one set that has cardinality 0 because every set either has some elements or it doesn't have any. And if it doesn't have any, well, that's going to be the only possible set with cardinality 0. So we call that set the empty set. The empty set is just a set with no elements, and we have some notation that we use for the empty set. Sometimes we use a 0 with a slash through it. Sometimes this is used as a null set. Sometimes they call it that. Or sometimes it's curly brackets with nothing inside. But either way, this is representing something that we call the empty set, a set with no elements. Now you want to be careful here. You can use this notation of a 0 with a line through it, or you could use empty brackets, but you can't use both, right? If you have curly brackets with an empty set inside, this is really saying this is a set that contains one single set as this element, right? Remember, a set can be an element of a bigger set. That's what's happening here. This on the right-hand side represents a set containing the empty set. Sometimes it's useful to think about a set as being a box with some stuff inside, right? Up here, the set E contains the number 2, right? It's a box containing the number 2, the number -5, and a box, another box with some numbers inside. The empty set is just an empty box, right? But over here, what we have on the right-hand side is a box with another empty box inside, right? So technically, on the right-hand side here, this set has one element, namely the empty set itself. On the left-hand side, this set has no elements. So these aren't the same, and if you want to talk about the empty set, make sure you're using just a 0 with the slash in it, or just empty brackets, but not both. Okay, now our last definition is, what does it mean for a set to be finite versus infinite? Because we said on the last page that some sets are infinite. So we say that a set is finite if the cardinality of that set is equal to n for some natural number n. So as long as there's some natural number that describes how many elements are in that set, then we say that that set is finite. And if your set is not empty and also not finite, we call it infinite. So as an example, the natural numbers are infinite because you can't describe the cardinality of them using any single natural number. Similarly, the integers are infinite, the real numbers are infinite, there's lots of infinite sets.